Hi, let us solve some questions regarding heat exchangers. In the previous video, I have explained the topic heat exchanger in a very concise way, and I've also told you all the formulas and all the important points regarding heat exchangers. So let's take on some questions regarding the heat exchangers topic. So the first question is the radiator in an automobile is a cross flow heat exchanger. Okay, don't get confused by this term cross flow. Just read the question. Oh, let me change the point. Yeah. So don't get intimidated by this term cross flow heat exchanger. Just read the question. Because we study only parallel flow heat exchanger and counter flow heat exchanger in detail. So just read the question first of all. So it's a cross flow heat exchanger UAS. Okay, this is given. Is given as 30 kilowatt per Kelvin. Okay, so this is 30 kilowatt. Make it in watt. Try to work in SI units. Okay. The engine fan draws 30 degrees Celsius air through this radiator at 10 kilogram per second. Okay. So Cp of air is given 1 kilojoule per kilogram Kelvin. Change it in joule per kilogram Kelvin. And the mass flow rate of air is 10 kilogram per second. Okay. While the coolant pump circulates the engine coolant at a rate of 5 kilogram per second. So Cp of coolant is also given and the mass flow rate of the coolant is also given. That means from these two data we can find the heat capacity of air and heat capacity of coolant. Okay. The coolant enters this radiator at 80 degrees Celsius. Okay. So the entering temperature or the inlet temperature of this coolant is given. Under these conditions, what will be the number of transfer units of this radiator? Radiator. See, just in this question, you have been asked just about NTU. Okay, and there was no need to get intimidated by this term. So NTU is what? NTU is UA by C minimum. I've told you, I've explained this in the previous video. So NTU is UA by C minimum. Okay. How do you find this C minimum? So find the heat capacity of the hot fluid of both the fluids, and whichever is minimum will be C minimum. Okay. So let us find the heat capacity of air first of all. So that will be m dot A CPA. Okay, so this is m dot A, that is 10 kilogram per second, into CPA, that is 1 kilojoule per kilogram Kelvin. Okay, so that is 1 into 10 raised to the power 3 joule per, it is in kilogram per second. So this will be watt per Kelvin. Okay, this will be watt per Kelvin. And the heat capacity of engine coolant will be m dot C CPC. Okay, this is 5 kilogram per second into 4 kilojoule per kilogram Kelvin, that is 4 into 10 to the power 3 watt per Kelvin. Okay, so the data says, okay, this is what? This is 10 into 10 to the power 3 watt per Kelvin. This is 20 into 10 to the power 3 Kelvin. This is 20 into 10 raised to the power 3 watt per Kelvin. This is 10 into 10 to the power 3 watt per Kelvin. So obviously the heat capacity of air is C minimum. Okay. So put this value here. UAS is 30 kilowatt per Kelvin. So that means NTU is equal to 30 into 10 raised to the power 3 watt per Kelvin upon 10 into 10 to the power 3 watt per Kelvin. So that means NTU is equal to 3. Okay. This is the answer. Very basic question. Okay. Let's move on to the next one. Let's change the color. Yeah. So the flow rate of hot and cold water streams, both are water streams. That means Cp will be same. Running through a parallel flow heat exchanger. The heat exchanger is parallel flow, and the mass flow rate are given as 0.2 kilogram per second and 0.5 kilogram per second. The inlet temperature of hot and cold sides are 100 degrees Celsius and 20 degrees Celsius. Okay. The exit temperature of hot water is given. Calculate LMTD. Okay. How do you approach this question? Calculate LMTD. What is LMTD? LMTD is delta T1 minus delta T2 upon ln T1 by T2. Let's draw the temperature profile, the temperature distribution with distance x. What is this? This is parallel flow heat exchangers. So this hot water will lose heat, and this cold water will gain heat. And what is given? The inlet temperature of hot water is 100 degrees Celsius, and the inlet temperature of cold water is 20 degrees Celsius, and the exit temperature of hot water is 50 degrees Celsius. Okay. So delta T1, I know delta T1, which is 80 degrees Celsius. No need to change the temperature in Kelvin, okay? Because ultimately this is difference. Delta T1 is difference. So 273 Kelvin and 273 Kelvin will get cancelled out, okay? So no need to take Kelvin, the temperatures in Kelvin, okay? So delta T1 is 80 degrees Celsius. What about delta T2? I do not know the outlet temperature of the cold water. So what can I do to find this temperature TCO? Okay, that is outlet temperature of cold water. What I can do? I've told you that you'll have to apply energy conservation, because the heat lost by this hot fluid will eventually be gained by this cold fluid, because we treat that no heat is lost to the surroundings. Okay? We assume this in case of heat exchangers. Also, we assume that the pressure remains constant. Okay. So if you have doubt regarding that also, I'm telling you about pressure. We assume that pressure is remaining constant. Okay. So where we were going to apply energy conservation. Okay. So applying energy conservation, what will be this? This will be m dot h Cp H or Cp, whatever you want, because it will get cancelled out, because both the fluids are water. So delta T of hot water is 100 minus 50, directly writing it. 100 minus 50, this is delta T, which is equal to m dot C, Cpc. The temperature change of cold water will be TCO minus 20. Okay, this gets cancelled out. M dot H is 0.2 kilogram per second, and cold water is 0.5 kilogram per second. Put the values, you will get the temperature, the outlet temperature of cold fluid is, this will be 40 degrees Celsius. Yeah, this is 40 degrees Celsius. Okay, this is 40 degrees Celsius. So when this is 40 degrees Celsius, this becomes 40 degrees Celsius. What is delta T2? What is delta T2? Delta T2 will be 10 degrees Celsius. Okay. Now you have delta T1, which is this is 80 degrees Celsius, and delta T2, which is 10 degrees Celsius. This is 80, and this is 10. This is 10. Okay. You have all the data with you. Find LMTD, simple. And the value of LMTD will be equal to, giving you the answer, it will be equal to 33.66. 33.66 degrees Celsius. This is the answer. Okay. Let's move on to the next question. We'll solve some good questions. Okay, so this is in a counterflow concentric tube heat exchanger. The LMTD is 56 degrees Celsius. Okay, Now LMTD is given. So the LMTD is 56 degrees Celsius. So let me write it here. LMTD is 56 degrees Celsius. During a test run, hot fluid flowing at 0.1 kilogram per second and 110 degrees Celsius is cooled by cold fluid supplied at a temperature of 25 degrees Celsius and a flow rate of 0.2 kilogram per second. Okay, this is some data. So let us plot it on this graph. Is this a parallel flow? It's a counter flow. Okay, this is a counter flow heat exchanger. So this will be the profile. Okay, so what it's saying that the hot fluid, the entrance temperature of hot fluid is 110 degrees Celsius and the mass flow rate is m dot h is 0.1 kilogram per second. Okay, and it is supplied, it is cooled by cold fluid supplied at a temperature of 25 degrees Celsius. So this is the inlet temperature of cold fluid. Okay, counter flow. And the mass flow rate of cold fluid is 0.2 kilogram per second. So m dot c is 0.2 kilogram per second. This is given. Specific heat at constant pressure of the hot fluid is 4.2 kilojoule per kilogram Kelvin. So that means CPH is 4.2. I'm not writing the units here because there is less space. Let me write it. Kilojoule per kilogram Kelvin. And CPC is 2.1 kilojoule per kilogram Kelvin. Okay. So what will be the exit temperature of the cold fluid? So many of the students, what they will do, they will start energy conservation and other methods. But when this type of question comes and it's mentioned that it is a counter flow heat exchanger, first of all, always find, if you have been given with the data of this mass flow rate and specific heats, always find the heat capacity of both the fluids, because there is a chance that heat capacity of both the fluids can be equal, and if they come equal, what will happen? It will become a special case where LMTD is equal to delta T1 is equal to delta T2. Okay, and this will be straight line. Okay, so let's check the heat capacity of hot fluid. What is it? It's 0.1 into 4.2. The same, because the mass flow rate is just double and specific heat is just half. So I can directly say that this is same. This is equal. So this heat capacity is equal of both the fluids are equal. So CP is capital C is equal to CPC. Okay, and the value is what? The value is multiply the value. That's what this is. We don't need it. So these are equal. So it becomes a special case now. Okay. So in a counter flow heat exchanger, when the heat capacities of both the fluids is equal, becomes a special case. Only in counter flow heat exchanger. I've explained it in the previous video. So this is what these two lines become straight lines. Okay. So now this is a straight line and this is also a straight line. Okay, so they have asked us what will be the exit temperature of the cold fluid. That is, this will be the exit temperature. Let it be TCO. Okay, now I have LMTD with me. LMTD will be equal to delta T1 will be equal to delta T2 in this case only, because the heat capacities of both the fluids is equal. So this is delta T1 and this is delta T2. You can even find the outlet temperature of the hot fluid. You can even find that. but we have been asked what will be the exit temperature of the cold fluid. So delta T1 is equal to 56 degrees Celsius, and this will be equal to 110 minus TCO. This type of questions do come in GATE exam and other relevant exams. So TCO is what this is, 54 or what, 54 degrees Celsius. So it is 54 degrees Celsius. Okay. This is the answer. This is 54 degrees Celsius answer. You can even find the outlet temperature of hot fluid. Okay, because you have LMTD and delta T1 is equal to delta T2 is equal to LMTD. So you can find that also. Let's move on to the next question. Okay, the next question is, during open heart surgery, the patient's blood is data. CP is given. Is cooled before the surgery and rewarmed afterwards. Okay. For this purpose, a concentric tube counterflow heat exchanger. Counterflow heat exchanger of length 0.5 meter is used with the thin walled inner tube of 55 mm diameter. Okay. So be careful that in this question area may be used. Why? Because length is given and diameter of the tube is given, and area is the term that contains both these terms, that is pi dl, because heat transfer occurs through this surface area, of the tube. Okay, heat transfer actually occurs through the surface area of the tube. So area is pi dl. Okay. So diameter is 0.055 meter and length is 0.5 meter. The overall heat transfer coefficient is also given. That is U is also given. U is 500 watt per meter square Kelvin. Okay. If water at 60 degrees Celsius, Cp is given, and its inlet temperature is given, and its mass flow rate is also given, is used to heat blood entering the exchanger. The inlet temperature of blood is given and the mass flow rate of blood is also given, and 0.05 kilogram per second. What will be the temperature of the blood leaving the exchanger? Okay. All you have to do is firstly draw that temperature distribution, temperature profile. Okay. So this is change the color. Okay. So what it's given that the water at 60 degrees Celsius, and it is a counterflow heat exchanger. So water at 60 degrees Celsius, this is the inlet temperature of water, and blood entering at 18 degrees Celsius. So this is the cold fluid. Blood is the cold fluid which is entering at 18 degrees Celsius, and the mass flow rate of blood is 0.m.c. I'm denoting blood with actually I am denoting this with m.c. Okay, so m.c is what? 0.05 kilogram per second. Okay, and Cp of blood is 3.5 kilojoule per kilogram Kelvin. Okay, and Cp of water is 4.183 kilojoule per kilogram Kelvin, and mass flow rate of water is also given, that is 0.1 kilogram per second. This will be the hotter fluid, so let it be m.h. Okay. This is Cph, this is Cpc. Okay, now this is the data given to us. Now it is a case of counterflow heat exchanger. Okay, so what I've told you, that first of all check the capacity, check the heat capacities of both the fluids. Okay, so if you multiply this mass flow rate with specific heat capacity of hot fluid, I don't think they will come equal. Okay, let me check the values also. This will be, yeah, so CH in this case is CH, that is heat capacity of the hot fluid, that is water, is equal to 418.3 watt per Kelvin, and for blood, that is cold fluid, is equal to 175 watt per Kelvin. 175. This is 175 watt per Kelvin. Yeah. Okay. So we have to find the exit temperature of blood. Okay. So let it be TCO, and the outlet temperature of water, let it be THO. Okay. So what is the formula that contains the terms of temperature? Okay. What is that formula? Can I say effectiveness of the heat exchanger is that one formula? Is that one of the formulas that contain the terms of temperature and can be used here? Because we know two formulas of effectiveness. Okay. One is this one. One is this one. For a counterflow heat exchanger, this will be equal to 1 minus e raised to power minus NTU 1 minus C upon 1 minus C into e raised to power minus NTU 1 minus C. Okay. And I know every data. What is NTU? NTU is equal to UA by C minimum. C minimum. Do I know U? Yes, overall heat transfer coefficient I know. Okay. And area I can find out because I have been given with L and D. So pi dl is area, and C minimum is what? C minimum is this. This is C minimum. That is the heat capacity of the blood is C minimum. Okay. So I can find out NTU directly. So NTU is 500. Let me write the data. 500. Is it in watt or kilowatt? Watt. So 500, and this is pi D. D is 55 mm. Yeah. So 0.055 into 0.5, that is L, and C minimum is 175. So NTU will be equal to NTU is 0.247. 0.247. Okay. And what will be C? C is actually C minimum upon C maximum, that is capacity ratio. So C is equal to C minimum upon C maximum. If this is C minimum, this becomes C maximum. Okay. Take the ratio, and this C will be equal to 0.418. This is 0.418. Okay. Now I have NTU, the value of NTU, and I have the value of C. So put it here, you will get effectiveness. The value of effectiveness for this counterflow heat exchanger will be this will be equal to what? This will be what? This will be, where is the value? Where is the value? Yeah, it is 0.21. It is 0.21. Okay, so this is 0.21. Yeah. And the second formula that we know for effectiveness actually contains the terms of temperature. Okay. What is that? Effectiveness is equal to, let me change the color. Effectiveness is equal to Q actual, okay, upon Q maximum possible. And I have explained what is Q maximum possible equal to. This is equal to C minimum into THI, that is inlet temperature of hot fluid, minus TCI, that is inlet temperature of cold fluid. And what will be Q actual in this case? Okay, what you have to find, you have to find TCO actually. Okay, so yeah, so this is equal to 0.21. So if I have to find TCO, I will be using the terms containing TCO and TCI. Okay, that is the heat gained by the cold fluid, because this will be the only variable which will be remaining, that is TCO. Okay, if I will be using this term, that is m dot h cph 60 minus tho, what will be its use? It will be of no use to me because I have to find TCO. Okay, so m dot h cph 60 minus tho is actually equal to the this m dot c cpc tco minus 18, because the heat lost by the hot fluid is actually equal to the heat gained by the cold fluid. So this is cpc and this is tco minus 18. Okay, and coincidentally cpc is c minimum, so it gets cancelled out. Generally when it is the other way around, then like all the temperatures are given to us and we have to find effectiveness from this formula, what we do is we deliberately put that term, that expression in the numerator, so that c minimum and this cpc or whatever this term be, this gets cancelled out. We deliberately put that expression, but here we actually have to find the outlet temperature of the cold fluid. So we would be using this the expression containing this term only. So solve this. I guess THI, you know that THI is 60 and TCI is 18. So this is 60. This is 60 and this is 18. Okay, and everything you can find out the outlet temperature of blood, that is 26.8 degrees Celsius. 26.8 degrees Celsius. Okay, this is your answer. So we are moving towards some good questions. Okay. A counterflow heat exchanger is employed to cool 0.55 kilogram per second. Cp is given, mass flow rate is given of oil from 115 degrees Celsius to 40 degrees Celsius by the use of water. Okay, some data is given. So this is a counterflow heat exchanger. Okay, and this oil has to be cooled. So this is 115 degrees Celsius. Write it properly. This is 115 degrees Celsius and outlet is 40 degrees Celsius. The mass flow rate is 0.55 kilogram per second and CP H is 2.45 kilojoule per kilogram degree Celsius. Okay, and the inlet and outlet temperatures of cooling water are also given. So this is a counterflow heat exchanger. This and the inlet temperature of water is 15 degrees Celsius and the outlet temperature is 75 degrees Celsius respectively. The overall heat transfer coefficient is also given and it is expected to be, so U is 1450 watt per meter square Kelvin. This is given. Using the NTU method, the surface area required is, okay. So you have to use the NTU method, that is you have to use that formula for effectiveness in which NTU comes and NTU is equal to UA by C minimum. So you find NTU, if you find NTU you can find area. Okay. So NTU is UA by C minimum. Okay. In the exam it is generally not mentioned which method to use, but since here we are practicing, so I gave this problem deliberately so that we can practice this method. So using the NTU method, NTU is UA by C minimum. So if you find out NTU, you will be finding out area. Why? Because U is given to you and C minimum, you can find out C minimum. Why? Because I think everything is given to you. No, the data about this cold fluid is not given to you. We can find it. Yeah, we can find it. How? By energy balance. Yes. Yeah. So by energy balance, we can find it out. So let's use energy balance. Okay. Energy balance. So this, what is this C? Heat capacity of the hot fluid is 0.55 into 2.45 kilojoule per kilogram degree Celsius. I don't know what the value is. I don't know the value. So just multiply it, whatever be the value. Okay. And the second fluid is water. Okay. So generally in the question, the specific heat capacity of water will be given. Okay. If it's not given, you can take it as 4.18 kilojoule per kilogram degree Celsius. Okay. Apply energy balance now. So this will be 0.55 into 2.45 into temperature change of the hot fluid, that is 115 minus 40. So 115 minus 40. Okay. If it, and this one is m dot cold fluid, let it be m dot c, and CPC. CPC is 4.18 kilojoule per kilogram degree Celsius, because this is given in degree Celsius. Okay. So m dot c is this. Okay. There is one more method. If actually I didn't use this value of CPC, what we would have done, we would have written here capital CH into delta T. Okay. And we would have written here capital CC delta T. Okay. So eventually we would have been arrived at this result that we would be getting CC directly. Okay. Like I will show you how to get that. Or just let us do that only. Okay. Yeah. So CH delta T is what? 115 minus 40, which is equal to CC. And what is delta T? Here, this is 75 minus 15. 75 minus 15. Okay. So this you know, this every term you know, you can get CC from here directly. Okay. This was also useful for us, and we will get CC from here, and we know CH, so we can decide what will be C minimum. Okay. You can go like that also, or if you want to put the values, individual values, you can say that it is 0.55 into 2.45 into this bracket delta TH, which is equal to m dot C. CPC is 4.18, and again this 60. Okay, so here from here you can get m dot C, which is given to us, which is 0.403. M dot C is 0.403 kilogram per second. Okay, so now you can multiply this with the 4.18 and you can get the value of the heat capacity of the cold fluid. Okay, but from what I was doing, I was just directly putting the value of heat capacity here, and I would have gotten this heat capacity value directly from this equation. Okay, whatever be the method you want to apply. So we'll get that CH, the heat capacity of hot fluid, is 1.347 kilowatt per Kelvin, and the heat capacity of cold fluid will be 1.648. That's 684. This is 684 kilowatt per Kelvin. So this is 1.347 and this is 1.684. Okay. So we get to know that this is C minimum. Okay. So this is C minimum. Okay. So now what we have two formulas of effectiveness, and this is a counterflow heat exchanger. What? This is a counterflow heat exchanger. Okay. So now you have to use those two formulas again, because we have been given with all the temperatures, so we can find effectiveness. And secondly, we have the formula for effectiveness. That is there is a bigger formula. I will write it out. So this is 1 minus e raised to power minus NTU, 1 minus c upon what was it? 1 minus c into e raised to power minus NTU upon 1 minus c. Okay. You can find out c, that is the capacity ratio, which is C minimum by C maximum. Let me write its value. It is what it is, 0.8. Yeah, it's 0.8. Okay, so this is 0.8 and NT you have to find out, and this effectiveness also you have to find out. Effectiveness we can find out from this data. What is this? Effectiveness is C minimum THI minus TCI. THI 115, TCI 15, sorry. Yeah, so 115 minus 15, that is 100. So in the numerator, what will be writing? You can write the term heat lost by the hot fluid, or the term heat gained by the cold fluid, whatever you can write. But to simplify our calculation, we'll be writing that term which contains C minimum. Okay, so C minimum is of hotter fluid, so that is CH, and the temperature change of hot fluid is 115 to 40, so 115 minus 40. Okay, so this CH actually corresponds to C minimum, so this gets cancelled. Okay, so solve it. The effectiveness will be, effectiveness comes out to be 0.75. 0.75. Okay, this is 0.75. Now this is 0.75. Okay, and this C is what? 0.8. Everything you know. What you can do? You can find out NTU. Okay, find out NTU. Okay, I don't have the space. So find out NTU, and this will be equal to, what should I remove? I will be removing this energy balance. Yeah. So NTU will be equal to, when you solve it, NTU will be equal to 2.35. 2.35, and that is equal to UA by C minimum. Okay, this is UA by C minimum. So C minimum is, I found out C minimum. Okay, and 1450 is overall heat transfer coefficient. You can get the required area in meters square. Okay, so the answer to this question is 2.183. 2.183 meters square. That's the answer. Okay. Next question. So the next question is, milk enters into the heating section of a high temperature short time pasteurization plant at a temperature of 45 degrees Celsius and leaves at 72 degrees Celsius. Okay. The inlet and outlet temperature of milk is given. Hot water at a temperature of 95 degrees Celsius enter counter currently. That is a counter flow heat exchanger into the heat exchanger and leaves at 77 degrees Celsius. Let's plot this. Hot water is at 95 degrees Celsius, and the milk is cold, which enters at 45 degrees Celsius and leaves at 72 degrees Celsius. And hot water enters at 95 degrees Celsius and leaves at 77 degrees Celsius. Okay. No information is given about the mass flow rate of water or milk, and no information is given about the heat capacity of the milk. You can take, generally it will be given in the question paper that you have to take the specific heat capacity of water as 4.18 kilojoule per kilogram Kelvin. Okay. But since no data is given and you have been asked the effectiveness of the heat exchanger, that means this is clear. When all the temperatures are given, that means you have to use that formula which contains the terms of temperature. Okay, to use the formula of effectiveness which contains the terms of temperature, which is C minimum THI minus TCI. Okay, and in the numerator, what will be? It will be Q actual, and that can be C. This is hot, this is cold, so C, that is heat capacity of hot fluid, 95 minus 77, sorry, and is equal to Cc of 72 minus 45. Okay. This is Q actual. This is Q actual. Okay. but we have to put that term here so that the C minimum gets cancelled out with something above in the numerator. Okay. How can we decide that CH is minimum or C minimum or CC is C minimum? How we can decide? We will again be using energy conservation. See, when we use energy conservation, what happens? The heat lost by the hot fluid, that is CH delta T, that is 95 minus 77. 95 minus 77? Yes. 95 minus 77 will be heat gained by the cold fluid, that is CC. 72 minus 45. So 72 minus 45. So this is what this is 95 minus 77. This is CH3, that is 3, and this is 18. And this is equal to CC. This is what 5, 7, 27. Okay, this is 27. Can I decide now? Yes, I can decide. Which is bigger, CH or CC? Tell me. These two terms have to be equal. So if this is smaller, 18 is smaller than 27, that means CH has to be bigger than CC. Okay. So CH has to be bigger than CC. Okay. So that means CC corresponds to C minimum. Perfect. Now use this C. Now use the equation that has CC. That is the heat gained by the cold fluid. I'll be writing it in place of Q actual. So this is CC 72 minus 45. This C minimum and CC gets cancelled out because CC corresponds to C minimum. Now THI is 95. This is 95. So this is what? This is 95. And TCI is what? This is 45. And you have all the terms with you. Effectiveness will be equal to 0.54. 0.5. Nice question again, because no data was given regarding the specific heat capacities at mass flow rate. So again, this energy conservation is very important. Okay, this actually tells you. This will actually be involved in many of the questions that you'll solve in heat exchangers. Okay. So this is again a nice question. If you want to try it, you can try it yourself first. So if you have tried it, an air heater uses steam condensing at 110 degrees Celsius. Okay. Steam is condensing. So this is a case of steam condenser at a rate of 5. Okay. To heat air at a rate of 5 kg per second from 20 degrees Celsius to 75 degrees Celsius. It is desired to double the airflow at the same time achieve air outlet temperature of 75 degrees Celsius by increasing the steam condensing temperature. Great. The new condensing temperature is okay. So the outlet temperature has to remain same at 75 degrees Celsius, but what we require is we actually desire to double the airflow rate. And how we can do it? By increasing the steam condensing temperature. Okay, so let us draw this temperature distribution for the first case when the steam is condensing at 110 degrees Celsius. Okay, this is 110. This is 110. Phase change. Okay, so this is 110 degrees Celsius, and the air is heated from 20 degrees Celsius to 75 degrees Celsius. This is 75 degrees Celsius, and this is 20 degrees Celsius. Okay. Counter flow heat exchanger or parallel flow heat exchanger, you can take any of them because I've explained in the previous video. It doesn't matter whether it is a counter flow heat exchanger or a parallel flow heat exchanger, effectiveness will remain same because one of the fluids is undergoing phase change. Okay? It's a special case. So this is for the first case, that this is 110 degrees Celsius. Okay. Now for the second case, when we have to increase the steam condensing temperature. Let it be T. Okay, let it be T. So this is T degrees Celsius, this is T degrees Celsius. And again, the outlet temperature and the inlet temperature of the air will remain same. This is 20 degrees Celsius and this is 75 degrees Celsius. Okay. So how can I find out this T? How can I find out this T? Nothing is given about heat capacity, sorry, the specific capacity of the fluids. One more data is given, that is 5 kilogram per second. M dot A, in first case it is 5 kilogram per second, but in the second case it is desired to double the airflow, that is it will be 10 kilogram per second. Okay, so in this question we again have to apply the simple basic funda of energy conservation. Okay, so we have these three formulas for the heat transfer in a heat exchanger. First one is UA LMTD. Okay, this gives me the overall heat transfer rate in a heat exchanger, where U is the overall heat transfer coefficient, A is the area available, area of the heat exchanger available for heat transfer, and LMTD is LMTD we find out LMTD, that is log mean temperature difference. Okay. Second one is we can compare this heat transfer rate by the heat lost by the hot fluid. Okay, so that is M dot H CPH and delta TH. Great. And this heat lost by the hot fluid will be equal to the heat gained by the cold fluid, CPC delta TC. Okay. So this is how I actually can find out the heat transfer rate in a heat exchanger, okay, by these three questions. Okay. So for the first case, can I find out the LMTD? Yes, I can find out the LMTD because all four temperatures are known to me. Okay, so this is delta T1, which is 90 degrees Celsius, and this is delta T2, which is 35 degrees Celsius. So LMTD in first case will be LMTD in first case will be equal to what? Yeah, it will be equal to 58.238. So this is 58.238 degrees Celsius. Okay, this is for the first case. So can I say that Q is equal to UA 58.238? Yes, I can say that UA is equal to 58.238. Okay, and also I can say that the mass flow rate of okay. Also I can say that the heat lost by the condensing of steam is the heat gained by this air. Okay, this is used to heat air. Okay, so now can I say that this heat will be equal to M dot A CPA 75 minus 20, 75 minus 20. Okay, so this is this is equal to M dot A CPA minus 20. M dot A is 5 kilogram per second, 5 CPA, and this is 55. So this Q is equal to 275 CPA. 275 CPA. Okay. This is for the first case. Now for the second case, only this mass flow rate of air will change. So this will be Q for the second case. This will be M dot A CPA. Temperature is 75 minus 20 only. Okay, and CP is also same. So this will be 10 CPA 55. Okay, this will be 550 CPA. This is heat transfer in the second case when you actually desire to double the flow rate of air. Okay, but can I find out LMTD in the second case? No, I cannot find out LMTD in the second case. But I mean, I cannot find out LMTD from these temperature profiles. Okay. So what will I do? this Q2, which is equal to 550 CPA in second case, is equal to UA LMTD of second case. But one thing I can do, that this UA will remain same, and here from this equation, that is UA 58.238, I can find, okay, and UA will be equal to 275 CPA by 58.238. 275 CPA, this is 275 CPA by 58.238. 58.238. It's a bit lengthy question and it's a bit confusing one because you have to deal with a lot of data. But so this is how you will be finding LMTD for case 2. Okay. So this is what, this is 550 CPA. Okay, that implies. So CPA and CPA gets cancelled out. 550 into 58.238 divided by 275. You will get LMTD as, for the second case, you will get LMTD as 116.476. Now once you get LMTD, you can find out temperature. Okay. So let me summarize this question what I have done. So by energy conservation and by finding the heat transfer rate in a heat exchanger, these three formulas are used. You know this. Okay. So I've just used these two, or there is no significance of this hot here, but I've just used this formula and compared it with the heat gained by the air. Okay, so this also gives me the total heat transfer rate in a heat exchanger, and this will also give me the total heat transfer rate in a heat exchanger, that is the heat absorbed by this air that is entering. Okay, so in the first case I have equated them, and from that I got the value of UA because I know LMTD. In the second case, when mass flow rate has doubled, I have again equated both of them, and I have put the value of UA from this in the second case, and I've got the value of LMTD. So LMTD is 116.476, and in second case will be this is delta T1, which is T minus 20, and this will be T minus 75. So this is T minus 20 minus T minus 75 upon ln T minus 20 upon T minus 75. This T and T gets cancelled out. Okay, so take this ln here and solve it, and let me do it. So ln T minus 20 upon T minus 75 is equal to, what will be the value? So I guess it will be, I don't know, you can solve it. You know, it will be 55 upon this 116.476. Okay, this natural log, this E goes here and you will get some value. I'm directly writing T is equal to 166. You can solve it. 166.2 degrees Celsius. This is 166.2 degrees Celsius. So in an oil cooler, oil enters at 160 degrees Celsius. If water enters at 35 degrees Celsius, flows parallel to oil. The exit temperature of oil and water are 90 degrees Celsius and 70 degrees Celsius respectively. By increasing the length of heat exchanger, the minimum temperature which the oil can be cooled. So oil enters at 160 degrees Celsius and the water flows parallel to oil. So it is a case of parallel flow heat exchanger. This is 160 degrees Celsius and water enters at 35 degrees Celsius. By now I guess you must have, by now you can actually solve these type of questions, So the exit temperature of oil and water are 90 degrees Celsius and 70 degrees Celsius. This is 90 degrees Celsius and this is 70 degrees Celsius. Okay. By increasing the length of heat exchanger, the minimum temperature to which the oil can be cooled is. This line means that we can take the length of the heat exchanger to be infinite, and what is the minimum temperature of oil that we can achieve. Okay, so hypothetical case, increase it where the temperature of both the hot fluid and the cold fluid is same. Okay, so let there be a length at a very let there be a very large length where the final outlet temperature of the hot fluid and the cold fluid becomes equal to T. This you have to find. So the minimum temperature to which the oil can be cooled is. Okay, I have no information about their specific heat capacities. Let's use energy conservation. Directly using the energy conservation. This is m dot h cph and 160 minus 90, which is equal to m dot c cpc 70 minus 35. So this is capital CH and this is 160 minus 90, which is 70. So 70. And this is heat capacity of cold fluid is 35. So what is this? This is CH by CC is equal to 35 by 70, which is 0.5. Okay, so that means that the heat capacity of hot fluid corresponds to C minimum. Okay, and this is what? This is the heat capacity ratio which we have got. Okay, now we have to find the temperature to which it can be cooled. Again, apply energy conservation. Okay, because now we know the ratio. Now we know the ratio of both the heat capacities. So we can apply again energy conservation. So this is CH. And the temperature to which it can be cooled is T. So the initial temperature, inlet temperature of oil was 160 minus T is equal to Cc. The inlet temperature of water was 35 degrees Celsius and outlet is T, which we have assumed where both the temperature of both the fluids will be same. Okay. So CH by Cc is 0.5. Now we know the answers. This is CH by Cc is 0.5. 160 minus T is equal to T minus 35. Find out T. T will be equal to 76.7 degrees Celsius. 76.7 degrees Celsius. Next question. A condenser having effectiveness 0.647. Effectiveness is given. That means we have to use the effectiveness formula. Through tube of 25 mm diameter is also given at the rate of 0.05 kilogram per second. Mass flow rate is also given. The length of the heat exchanger, okay, you have to find the length of the heat exchanger if the overall heat transfer coefficient, this is overall heat transfer coefficient is 230 watt per meter square degree Celsius, and the specific heat of water is 4.18 watt. So it's kilojoule per kilogram. So we have specific heat of water, we have overall heat transfer coefficient. So and what else do we have? We have the effectiveness of heat exchanger. So let us write out. Effectiveness is 0.647. Okay, and this is a condenser. This is a condenser. So that means the fluid which is condensing is having C max. Okay, because the condensing fluid has its heat capacity which approaches infinity. So that means the water which is flowing will correspond to C minimum. Okay, its heat capacity will correspond to C. Okay, so this is sea water. So I have the mass flow rate. Yes, I have the mass flow rate of water, that is 0.05 kilogram per second, and also I have been given with Cp of water, that is 4.5. 4.18 kilojoule per kilogram Kelvin. Change it in joule, that is 3. So the value will be what is the value? Okay, no value is given. We leave it here only. So now you have to find the length of the heat exchanger. Tell me, in which formula length of the heat exchanger comes? NTU. NTU is equal to UA by C minimum. Okay, and area is the term where the term L comes, that is pi dl. Area is pi dl. So if I get NTU, I will get area, and area is pi dl. Okay, I have diameter, I will get length. Okay, so the process is clear to me. But how can I get NTU? You have been given with effectiveness. I told you by saying this value that you will have to use the formula for effectiveness. But the condition given here is condenser. So C is equal to C minimum by C maximum. C maximum is infinity, C is 0. Okay, and it doesn't matter if it is a parallel flow heat exchanger or a counter flow heat exchanger, because the formula for both are same. So I don't remember the formula. I'll put C is equal to 0. So let me write the formula for parallel flow heat exchanger or for the parallel flow heat exchanger. So this is 1 minus e raised to power minus NTU 1 plus C upon 1 plus C. Okay, so when I put C is equal to 0, this is 0. Okay. When I put C is equal to 0, this is 0, this is 1, 0, this is, so it becomes 1 minus e raised to power minus NTU. Great, effectiveness is given to me, that is 0.647 is equal to 1 minus e raised to power minus NTU. Can directly get out the value of NTU. Okay, so NTU is equal to, when you solve it, NTU is equal to, is it given? Yeah, it is given. So it is 1.041. Okay, so this is 1.041. Now you have NTU with you 1.041. Overall heat transfer coefficient is 230 watt per meter square degree Celsius. Area is pi, put the value of D, that is 0.025 meter. Take care of units. DL upon C minimum. Okay, this is C minimum 0.05 into 4180. 4180. Take care of the units. Please try to put all the values in SI units. Okay, it will be beneficial for you. So L is, it comes out to be 12.04 meters. This is the final answer. I guess I've solved enough questions for you and covered all the important concepts regarding heat exchangers. Okay. So this is how you solve the question of heat exchangers. So option is, okay, this is an option also. So I guess these that theory video and this numerical video will be enough for you to revise heat exchangers. Okay, and that's all from my side for heat exchangers. Thanks.